Okay, so for the final part of section 6.4 here, we actually have a pretty tricky example. So astronomers discover a binary star system with a period of 90 days. Both stars have twice the mass of the sun, so 1.99 times 10 to the 30th times 2. Right, that's the mass of our sun. And then how far apart are the two stars? So they're asking us to write for the separation between these two equally massive suns, these two equally massive stars. Like I said, this is actually a pretty tricky question, and you guys will see a few of these as you go through the homework. And anytime we have a binary star system, it gets a little bit more complicated. We can't just, for instance, use like our period equation of 2 pi and then the square root of r cubed over gm. We cannot just use that, right? It actually has another twist or two in here. But first and foremost, let's make sure we can kind of set up this scenario. Okay, so you've got one star over here, you've got one star over here. Right, so that's what the binary star system's got at play here. Right, so as these two rotate, well, each of those stars would rotate around their common center of mass. And so the key here is the two masses are the same mass, and so the center of mass is going to be that arbitrary point right between them, right? So we're going to have this distance of, let's call it r over here, and then this distance of r here as well. And again, it actually is a very key concept that they have the exact same distance between them. Right? If I told you that this massive was twice as heavy, we know the center of mass would actually be closer to that heavier star, and that would again change this problem a little bit. Right? But the way that a binary star system works is each of those two suns, each of those two stars, is going to orbit, it's going to oscillate, or not oscillate, but orbit, it's going to move in a circle around the center of mass. Right? So let's just say hypothetically both of these are then moving in the counterclockwise, or rather clockwise direction, I should say. I should probably pay attention to my arrows as I'm drawing them there. But anyway, so we've got these two stars that are moving in clockwise direction around that common center of mass. So again, they follow kind of a circular path that was a terrible circle, but they follow some type of path that looks something more or less like that. So then how do we approach these problems, right? What's the approach? Now this one actually you could simplify a little bit. However, the generic approach is always going to be very similar to what we would normally do. Right? We know that each of these two stars is moving around in a circular orbit. Right? So we know that each of those two is moving in a circular orbit. And in order to move in a circular orbit, they have to have a centripetal force. And much like we've done for any of our satellites, if we look at the centripetal force, the key concept here is we've got to identify what force provides the centripetal force. And as often is the case, it is the mutual force of gravity between the two that's providing the centripetal force. So my centripetal force is coming from the force of gravity between the two objects. Here's where it's different. Normally when we break this up, this would be mv squared over r equals g m1 m2 over r squared. Now it looks completely like what we would normally do, right? The difference though is what represents the r. Right? When we talk about centripetal force is referring to the distance from the center of the circle. Right? So if I was focusing on this as star 1, then as this moves around in the circle, the distance from the center of the circle would just be that single r, right? So this is truly then just r. However, when I talk about the force of gravity, right, it's not the distance around the center of the circle, it's what's the separation, what's the distance between the two. So this r is not actually just a single r, it's actually 2r, right? So I'd have to take 2r squared because it's the entire separation between these two suns. It's the entire distance between those two suns. And that's where the biggest difference comes into play. Right? The centripetal force just comes from the circular path, whereas this r over here represents the entire distance between the two objects. And so we unfortunately cannot just cancel out one of the r's, and we cannot just get to the period equation we've seen once before. Instead, we have to get a little bit more clever with this, right? Now this mass would still be whichever star we choose to work with. So let's just say again this is mass 1 here. Right, so I'm choosing to work with star 1. So that mass would cancel out, which leaves us then with the other mass, which just so happens to be the exact same thing as our first mass. And then velocity and the distance here, and then I'm calling this 2r because it's the entire separation. Right, so now the key becomes how can I use the period, which is the information they gave me. They said that the period is 90 days, which obviously we can convert to seconds. And when I convert that to seconds, I end up getting, I'll go ahead and write that number down. I end up getting 7776000. Okay, so 7,776,000 seconds is how many seconds are in 90 days. Right, so I've got that number to work with. how can that help me with this equation here, with this relationship? Well, the period represents how long it takes around to go in the circle, right? And if I think of the velocity as 2 pi r, the distance over the period, then I can kind of work backwards and I can solve for, or actually just substitute this in for the velocity and then see where that goes. So that's what I'm going to do. I'm going to plug that in up here for the velocity. So I've got 2 pi r over t, that whole thing squared, and then over r, and then equal to on the other side of my equation. I haven't really done anything yet, right? So g m2 over, I'm going to go ahead and make the denominator 4r squared, right? So I went ahead and squared out the 2r quantity there. Right, so at this point it's really just a little bit of cleanup and plugging in the measurements that we know. So distributing the square to everything there, I get 4 pi squared r squared, but one of the r's is actually going to end up canceling out. So 4 pi squared r over, and then in the denominator I'd have t squared. Right? Over here I've got g, I've got m2, and then I've got 4r squared. So at this point, if I look at everything that I know, well, this is representing the same r, since I've already counted for that being 2r. That is now in terms of the same r. So the only variable that I have in this entire equation is that r. Right? So it just becomes an algebraic expression at this point. So 4 pi squared times r, and then I'm going to go ahead and multiply both sides by the 4r squared as well. So times another 4r squared here, divided by the period, so again 7,776,000 seconds squared, equals, on this side I have my universal constant, 6.67 times 10 to the negative 11th, times the mass of that other sun, which again was 2 times the mass of our sun, so 2 times 1.99 times 10 to the 30th. That is 2 times, not 2.1.199. That wouldn't make any sense. But anyway, so at this point here, obviously we've got r times r squared, so r to the third, and then we just need to try and solve the rest of the way for r. Right? So all we have to do is solve this out for r. And hopefully when you do so, I'll go ahead and write down the answer that I get here. So 4.67 times 10 to the 10th meters. So that represents my r. So then the only thing we do have to consider is, have I actually answered the question or not yet? Right? And if I go back up to the question, how far apart are the two stars? Well, I just found the radius, right? I found the radius from the star to the center of gravity to be r, which is 4.67. I need to double that, though, to find out the distance between the two stars. Right, so I'm going to take that number and double that, and that will give me my final answer, which gives us about 9.34 times 10 to the 10th meters. So there is the separation between the two binary stars. Okay, so again, I'll go ahead and recap here because I do have a minute, and I think it's worth it on these binary star systems. Right, so you'll see a few in the homework. Let's suppose that maybe we had like a star over here that was 2 times as massive, and a star over here that was just 1 times, right, as massive. The first and foremost priority would be finding the center of mass for the system, right? And so finding the center of mass for the system, right, is where I just do mass 1 times position 1 plus mass 2 times its position divided by the total mass of the system, m1 plus m2, right? And in this case, if I did that, I'd find out that the center of mass is half as close, right, to the heavier one. So if this distance is r, then this distance here would be 2r. Right? So then when it comes to the orbital motion, well, I'd have 2 choices, right, depending on which star I work with. If I chose the heavier star is going to follow an orbit. You can't really see that yellow there, so let me find a better color. Right? So the heavier star is going to follow an orbit with a smaller radius. So it's going to look something like that with just a radius there of r. Right? So the centripetal force for the heavier star would still be coming from mutual gravity between the two. This would be mv squared over just a single r equals g m1 m2 over what's the total distance between both stars. Well, the total distance between both stars would be that total 3r. Right? So again, we can see that the distance here would not be the same. Right? So again, that's the key concept, that's the key relationship. As soon as you guys can get comfortable with that fact, these problems actually aren't too bad to work your way through. But it definitely is making sure you're comfortable working through. And if this is something that does give you trouble, and I certainly understand if it does, I know the videos sometimes are hard to explain and answer questions. So if it does give you trouble, come find me and let me know. But this is something they would expect us to be able to manage, and something I hope you guys get comfortable with.